All right, the first thing I want you to understand is that on the exam, you're not going to be given the unit, meaning you still have to figure out that this is a statics problem. So of all the things that we study in physics, which indicators here let you know that, well, I should probably use statics as my means of solving it? And there's clearly a couple of things I think are indicators that I would use in narrowing it down. I mean, tomorrow, you don't need that, because you know tomorrow it's going to be a statics question. Goodbye. But on the exam, it's going to be full of all sorts of stuff. And you need to know when statics is what you need to use. So there's two major indicators here that this is a statics problem, or at least a force problem. And that is, first, I asked for a force. It's a huge indicator that I want you to use something about forces. And again, in your notes, something that's useful to know is that forces are really good at telling you the size of a force or the size of an acceleration. And when I say forces, I mean Newton's laws are really good at telling you the size of a force or the size of an acceleration. You're asked for force, so that should trigger Newton's laws. Second, the system is at rest. That's another indicator that force is probably where to go. Every other thing we've studied is dynamic. Something is moving, something's accelerating, there's a collision, there's changing height. This system's at rest. There's only one set of circumstances in which we study things that are at rest, and that was Newton's laws type 1 problems, where net force is equal to 0. So those are two good reasons why this should steer you towards a net force problem. Now, the next thing that I think you should do is when you realize you're going to be doing a net force problem, we're going to have to break this up now into two parts. Because before we only had forces to deal with, but now we have force and torque. So there's the net force problem first. I'm not going to go through all of the steps to solve a net force problem. You have information, you have all the steps. There are a few differences. I'm not drawing a free body diagram. I'm going to use this diagram instead because where the forces act is important. So that part's a little different, but everything else is the same. Start by identifying your object. Start by labeling the forces that are acting on it. Decide whether it's a first law problem or a second law problem. All of those things are still part of what we're doing here. So the net force problem, we decide if it's first or second law. Choose a direction to call positive. Identify all of your forces. Including the direction. Then you're going to employ either net force equals 0 or net force equals ma. That's just a banner overview, and you guys know this, so this is not new parts. So I'm going to identify upwards as my positive direction. I'm going to recognize that two forces have already been given to me, but there's a force that has not been displayed. I'm going to display that force. That is the weight of the meter stick, which we know to be 0.9 newtons. And I know it acts at the middle. And although I don't need that for forces, I need that right now. I'm sorry, I don't need that for force, I'll need it later for torque. And then I know it's a net force equals 0 problem. So I'm going to employ net force equals 0. And I'm going to say TL plus TR minus 0.9 equals 0. and set this aside. I can't solve this for either TL or TR. There's not enough information there. So although this gets me started, it doesn't solve my problem. So now I'm going to set the problem aside and go to the next portion. There are a few more things we have to do with the net torque problem that we didn't have to do with the net force problem. I'm just going to set this back up so I have a diagram. But we're still going to ask several similar questions. So A, is this a first or second law problem? Now that's easy for us right now. We've only talked about first law torque problems. But that ends in a day or two. So we know this is a first law problem. But for torque, there's more that we have to do. So one of the things we have to do is decide this is an important question. This is a distinction. It can be a first law problem and be moving. But if it's spinning, it already has an axis of rotation. If it's not spinning, we can choose the pivot point. Now, I'm not going to put all that in there, but I'm going to put some of that in there. You should put that in there too for the problems that are going to be spinning in a day or two. So A. The word here is static. So if it's one where we can choose the pivot point, then I've told you already, choose a pivot that eliminates a force. Well, I'm sorry, eliminates an unknown. None of this is new. These were your notes yesterday. I'm just afraid yours are clearly not organized enough to do this. Now, because ours is static and because we can choose our pivot point, we can place that pivot point anywhere we want, anywhere on the object. If we place it here at the middle, there's nothing wrong with placing it here, except I eliminate a force that I know. It's a known value, and it's going to give me two unknowns in my answer. Now, I can still use that. I'll have two equations and two unknowns, but that's going to make the math harder. You want to make the math as easy as possible, so if I place the pivot, say, here, well, I'm eliminating this unknown because the torque arm distance is 0 for this particular force. So based on this pivot point, that force applies no torque. So that's what we're doing. We're going to place the pivot point at the location of an unknown force. That way we eliminate that torque. Now, once you've chosen the pivot point, you need to assess the lengths of the torque arms. This one's going to be easy because we're setting our pivot point at 0. The lengths of our torque arms will be given, 50 and 60, because they were already written for us. It's on a meter stick. So part C, this is where we start actually, well, I guess I'll come back out. Once we've done all that, we can go to B, because this is where a big thing happens. You're going to list out all your torques. And I'm telling you to do this in a specific way. List them vertically. Right? Just list them all out vertically. Our goal is to be able to add them up so that we can set them equal to 0. So what this means for us is I'm going to have the torque due to the weight of the meter stick, and then the torque due to the tension on the right. So I'm listing them all out vertically. And then in the future, we're going to have more to this, so I want to make this flexible for us. If our system is accelerating, then we would set this equal to inertia times acceleration. But right now, we're doing static problems, so this will be set equal to 0. And I mean physically draw a line, put a plus sign, and remind ourselves, does this equal 0? Now, we will have to choose a direction for positive. There's actually more than one way you can do this. For a problem like this, where we're all looking at it together, you can just say clockwise and counterclockwise if you feel like it. Yes, you could use the right-hand rule and say maybe out of the board is positive. But you can actually still put a coordinate system on it and make this the positive direction, and this the positive direction, and this the negative direction, and this the negative direction. That will still work. If you'll notice, both torque arms will be in the positive direction, but one of the forces would be negative and one of the forces would be positive. That still works if you want to use something like this. This is how your textbook does it. I don't, but this is how your textbook does it. I generally just look at it and say, well, this force is making it go that way, and this force is making it go that way. And use that. But we can use the right-hand rule, and that works too. So if I say out of the board is positive, well, the weight is causing a rotation that is into the board, this way. Torque arm times weight, into the board, this way. I can use my right-hand rule. And my tension on the other side, out of the board. That one's going to be positive. But you'll have to find a way to differentiate whether one torque is positive or the other torque is positive. So based on what I just did, the torque from the weight of the ruler, negative, and the torque from my string, positive. You can do it your way, that's fine. Now we need to flesh out our torques. What I mean by that is flesh out the expression for torque. The whole R times F times the sine of the angle. That's specifically what we're talking about. R times F times the sine of the angle. So I'm going to go torque by torque and do this. Let's start with the first one. The first torque is the distance of 0.5 meters away from the pivot point, 50 centimeter mark. The size of that force, well, it's the weight of the meter stick, 0.9 newtons. And the weight's downwards, and the torque arm is to the right, so that's a right angle, so sine of 90 degrees. Go to the next one. That torque arm length is 0.6. All right, 60 centimeters away from the pivot point. The size of the force is unknown. And it looks like it's straight up, so all right, that's it. So the last part is sum your torques and generate a new relationship. want to make sure it's explicitly clear that Newton's laws provide you a framework to generate a relationship that may or may not solve your problem. You're hopeful that it will, but that's all it does is generate a relationship. What you do with that relationship determines whether you solve the problem or not. This is 0. I'm going to add up the torques. 0.5 times 0.9, 0.45. 0.6 times TR, so plus 0.6 TR. That's it. I generated a relationship. Now, I made a point of writing all this down very explicitly, but there's nothing I didn't say yesterday that's here. So I want to be, but we have two things now. We have this and we have this. And that's what it gave us. Ultimately, all those steps, everything to here, gave us two relationships. Can these two relationships be used to figure out TR and TL? And I easily can. I'm probably going to use this one first to solve for TR and get 0.75 newtons without the unit. It's not right. Then I'll plug it in here to figure out TL, and TL's got to be 0.15 newtons. Any questions? We'll see. Try again. All right, so I got a person standing on a big plank, plank's on some cinder blocks. I've given you some details about where everything is. I'd like you to tell me how much force do the cinder blocks push upwards to keep the plank from moving. This is the same problem except normal force and not tension. In fact, I'd argue this is yesterday's problem, where we hung a weight somewhere between two suspension points. Same thing. But I want the normal force that each cinder block provides to the plank. You guys follow what I'm asking for? Okay. You can assume the plank is of uniform mass, so its center of mass would be where the 20 kilograms should go, the middle.
Oh, so I see what you did. Look. Yeah. So you gotta use this relation. The point that you chose to eliminate because it's not 5 here. Oh, yeah, like right here. Actually, hold on. Right here. So you gotta use it in relation to this one. So in this case, you use 2 meters right here. Yeah. And then 5 meters. 200. 2 meters is here.
So you guys do something like this. 4 forces total. Any question about this? There's questions? What's your question?
Because the force is easy, that's just the. Yeah.
Can you explain to me how you got the 3 and the 2 inches?
Okay, so for the weight of the block, the plank, it's gonna be in the middle. So you're gonna be, plank is 10 newtons long, the middle's 5. Your pivot point is 2 inches in. But then wait, not the person, think of the thing, it's in the middle, it's 2, the block is, your pivot point is 2 inches in. So that makes sense. That makes sense. And then the 2 is your person, it says the thing's 2, not the.
Well,
No, every time it would be 5, but the pivot point is already 2 meters in.
weight, right? But the weight from
Oh, yes, yes.
here, because the middle of it is right here.
Yeah.
So you have, what is it? So the 200
So
you're
then
pushing down here.
60,
So you have 600
you're starting from there and it's
that
only 2
makes it
inches.
one. So you have to have, so you have tension weight and then of the humans. And then tension on the right.
So you're already 2 in the middle, we're gonna move more away.
Wait, I'm like 20 off.
But the, wait, I don't get the 5, you understand the thing for this one. Oh, wait, I don't get that. So the 5, so this is TBR is the one on the
So
right,
wait,
we're
so
at the
what?
one at the left.
3?
We got 2 on this side, we got 3 on this side,
Why the 10
that's
meters?
5, we got, so the whole thing is 5, so it still has to be 5.
And then TR would now
So you guys have to think about it.
PTR.
Unfortunately.
Um,
And then,
I think if I would have remembered that the whole thing was.
I mean, you can always like draw it out, you start and you establish, okay, this is 2, this is this, this is 5, this is this.
I actually knew what I
Big
was
little.
I got it right back.
I need I think I'm gonna work on the most negative side.
Oh, I see what I did. Okay. So if this is 3 meters, then it's 7
I
meters
said
right
up was
here.
positive, I said down.
Oh, I swapped these, but I still got right. That's fine. So this should be 2 meters.
200 and 600, those ones are down.
And then,
All right, so there's only 6 minutes left, which doesn't give me a whole lot of time to correct some things, but are there any questions about where these things have come from? All right. Then that means normal force from the left side cinder block plus normal force from the right side cinder block minus the person's weight minus the plank's weight has to equal to 0. This is the net force equals 0 equation. Any question about that? I'm going to choose a place to put my pivot point. I can choose anywhere I want, but I think there's an obvious choice. I'm going to choose to place my pivot point here. Any question about that choice? That means there will be a torque from the person, a torque from the plank, and a torque from the right support. Any question about that? These have to sum up to be 0. So I need R for each of those, F for each of those, the angle for each of those, and whether they're going to be positive or negative. I'm going to make this the positive direction. Any question about that? All right. This length from here to the first force is 2 meters based on the diagram above. So 2 times a force of 600 times a sine of 90. Any question? this distance, which goes to the middle. The middle is probably 5 meters from the end, so that's 3 meters from this support. That all good? I'm thinking the middle of the board is 5 meters from here. So it's 3 meters from the support. Times 200 times the sine of 90. Looks like to me the other support is 5 meters from here. But this torque is going to be in the opposite direction. Any question about where any of that came from? Just setting up a chart to organize myself. 2 times 600, 1200. 3 times 200, 600. Minus 5 NR. Just added it all up, set it equal to 0. Now, I do have to solve this so I can get something, but I have 2 relationships now. This one and this one. The bottom one I can just solve. All right, 1200 plus 600 is 1800 divided by 5. Any question about that? So that's got to be 360. I think my math is right there. Now if I want NL plus 360 minus 600 minus 200 equals 0. So NL equals 800 minus 360. So NL equals 440. Well, that leaves us 30 seconds. Probably not enough time to learn something else.